And today we'll talk about PRGs for low degree polynomials over the so let's start with the difference between polynomials over finite fields and polynomials over the rings. So what's the polynomial? X equals sum I times x of I, where I is a multiset, right? You can have x1 squared minus 2. So I like set 1, 1. And this is over all I. This is a degree D polynomial. And over reals, we know how to fool such polynomials. We use dy is independent, set, and it completely fools all degree D polynomials because completely fools each monomial, right? Because when you have at most D variables, it behaves as truly random bits. Over F2, so there's no meaning to taking power larger than 1, right? Because 0 to the power of 2 and 1 to the power of 2 is just the same. So in F2, it will be sum Fi, and this is in F2. Can't be too crazy. And this is then the size of I is at most B, but here it's not a multiset, it's just a set. Okay? And which functions are the linear polynomials, degree 1 polynomials over F2? We already met them earlier in the course, gave them a name, but let's see it's the same. Characters. What? The characters, right? What's a character? Chi S of x is just sum, and this now lives in F2.
When you say sum over I, you don't mean all of the I, right? Even some i's.
No. F5 is 0.
Okay.
So sum xi, this is just the same as -1 to sum xi, but this is in the ±1 writing, and this is in the 1, 0. Okay. So so the linear functions over F2 are the characters. We know how to pull the characters, right? That's epsilon mass. But how about higher degree polynomials? If we try to plug dy's independent sets, it doesn't help us. If we take the n-1 independent set of all even words with even weight, okay, it's easy to see that it is n-1 independent because you can fix the first n-1 bits and then only the last one is determined by the previous ones. And if you plug it into parity, which is a character, right? It's just the character with S, which is 1 again. So it doesn't fool parity. It's parity always says 0, while the average is half 1. Okay, so polynomials over R and over F2 are different, and we now want to construct PRGs for polynomials over F2. They do share an important fact that you can derive polynomials and get lower degree polynomials. Okay, so if you derive a degree D polynomial over the reals, you get a degree D minus 1 polynomial, and this is going to be true also over F2. And they still need to define the derivative over F2, but it's going to be true. So let's formally write our goal for today and define the derivative over F2. So what's a PRG for polynomials over F2? So PRG is a small set, as small as possible if we can, a small set S, such that the expected value of S is close to the expected value of F on the uniform prediction, most epsilon. Okay, and it will be convenient to work with functions to plus minus 1, so let us write one. Yes. Okay, in this writing, I mean expectation over S when X is sample of this. Yeah. You have a question?
I think so. Just as for the terminology, typically we said PRG is function. So in this sense, it would be S would be just the image of this function, like, because you need to.
Yeah. Okay. So if you, I think of a PRG as a set, but I think it's like in coding theory when you have the message and then the code. So the important thing is the set,
Right.
and the like moving from the seed to the set is the equivalent part to encoding or coding. Okay, so this is just another formulation of the error when we talk about plus minus 1 functions instead of 1,0 functions. And we want to find S as small as possible. For this should happen for all V. Okay. So the size of the set will depend on the degree. So if D equals 1, we know how to do this. That's epsilon by epsilon, right? Okay, let's define the derivative.
It's half that, not half minus half that.
I think it should be like this. Okay, so let's define the derivatives over F2. Okay, so we call it a directional derivative. So we choose a direction vector y.
Another question. N is also for
Yeah, S will depend on N and on B. So we choose y in F2 and we define the directional derivative in direction y of F. This is a function. It is just F of x plus F. Where does it come from? So over R, we choose a vector. And we find then F of the R, then V is the limit. F of x. It's familiar. This is in the
Oh,
never mind. It's, okay, so we so just take this one and then the x plus TV is the is what we plug here, and in the denominator we can have 0 or 1, so we just plug 1. this is the derivative, and the fact that derivative reduces the degree is not trivial, but it's improved. So it's like it. It's minus or plus. So yeah, so we're walking over two. So why does it reduce the degree? So let's write f of x equals sum f I x I and that's y. And now take the summation out. They have x to the I, plus x plus y to the I. And I open this up, so it will be sum over all j subset of I, x to the j times y to the I minus j. Right? So far, so good. And so this will be, we have an element from x to the I, and all the other elements are subsets of I, which are proper subsets of smaller size. Okay. Okay, so this term cancels this term, and all the powers of x are now of lower, smaller size. So the directional derivative reduces the degree also over x2. Okay.
Interaction that the function found. So.
I think it should become zero. The function should become zero. Okay, so let's take some additional facts and notations that we need on the way, and then start the construction of the PRG. So 3 bullets.
It's clear that it works, the binomial thing. I mean, we have vector, right? The x and y are vectors, the I is a set, so like it's not
like this is like a product over I x plus y I.
Yeah.
Right?
Yeah.
And then you have like all the parentheses, and you need to choose from each one x or y. Okay, so bullet 1, adding bias sets reduces the bias. What that means, so y is epsilon biased, it's that y1 plus y2, which are two independent copies of y, is epsilon squared bias. So you just sample y, and then you sample y is a random variable, and you sample it once, and then you independently sample another one. So this improves the bias, and it's not very good because it's also requires much more randomness, right? But how to improve this?
but it's linear in the randomness and quadratic in the part. So it sounds good.
So the seed length is linear in the
original one, the bias is working.
I mean, if you would have want the epsilon square bias, you would better construct an epsilon square biased set. You have a more efficient way than taking two independent.
Y is random variable, you mean Y is like, you have a set, that's one by itself, and Y is like a sample from that set.
Yes, exactly.
Okay, and if you take two samples and add them, it's better.
Yes. Okay. And this is one line now. So like this. And this is also true with more than two variables. So yi equals 1 to d. Same as what's this?
The
Bias in the character. So epsilon bias set needs to fool the characters. And the character has average 0, right? It should be minus the expectation over the uniform distribution of chi, but this is just 0. So I don't write it. And this is the same as chi on the sum, it's just chi is a character, it's a multiplicative function. Expectation of over the right is right. And the independence gives us takes the product outside, and this is most epsilon.
Why do you want to post this in IS? Isn't it like,
Should have for all the yes.
oh,
Yeah.
yeah, it's just like the same, but
Oh, yes, so. Okay. Put it on the blue. I think we just notation. So f plus y is just the shift of the function f by y. And we say that a class function f is closed under shifts if I can take any function f in f and shift it and stay in f. Okay, so applies f plus y also in f or y.
for any y not specific.
Yes. And this is just a notation. So the f for a class of functions, this is just the directional derivative of the functions in f in all the directions. Maybe I should do 0. I think I don't. Okay, so this is just a notation. And here's the idea of the construction of the PRG. Okay, so we will construct the PRG, and we will construct. We have a PRG for degree 1 polynomials. We will construct from it a PRG against degree 2 polynomials, and so on. Here we get the PRG for degree D polynomials. Okay, so generally think of W as a PRG that we constructed for degree D minus 1 polynomials, and we have Y an epsilon biased set, and we're going to combine them to get PRG for degree D polynomials. Okay. So here's the lemma. So suppose W holds the pairs with no, gamma. Y is delta bias. And we also need to suppose that F is closed under shifts. Okay, this is a very general proof about all classes curly F, and but you can just think about degree D polynomials, and then the derivatives of these polynomials are at most degree D minus one. Okay, so it's very general, but you should think of F just as degree D polynomials. So suppose F is closed under shifts, which we know that polynomials of degree D, if we shift them, we still get the degree D polynomials. And this can be seen the same way we had before with this proof. Okay, so it's closed under shifts. And suppose W folds the derivatives of F, which are gamma, it folds degree D minus one polynomials.
What's D minus one?
So if F has degree D polynomials, then we look at the derivatives.
So what is the derivative D minus?
Yeah, so the derivation reduces to the degree of polynomials. This is 2 over the reals and over F. That's what we show. Right, so we started with summation over all I, such that the size of I is at most D.
Right.
And we see that here, this term that comes from here cancel the X to the I, and we are left only with J, which are quarter subsets. Okay. Suppose this, then W plus Y equals F with gamma plus delta. Okay, so think of this as small. How are we going to construct the PRG? What is the form of the degree D PRG if we recursively open it? So just y1 plus y2 plus yd. So this is going to be the PRG that pulls the degree D polynomials. We have this term, we can already analyze the error, but I don't think we're going to have time for it, so let me keep it to the end. Okay, and the proof of the lemma is divided to 2. Any questions so far?
So in the beginning of the process, both gamma and lambda and delta would be epsilon. First step. And
So you it's just parameters. Well, it's not very interesting. We'll do it if we have time. Okay, so we define the imbalance of the function f as minus 1 over f. Okay, so if f is perfectly balanced, this is minus 1 half of the time and plus 1 half of the time, and the imbalance is 0. And if f is perfectly unbalanced, means that it's constant. So this is the imbalance is 1. Okay. And we prove the lemma by proving that w plus y pulls balanced functions and balanced functions separately. Okay, so lemma w plus y pools. F, like, F. No. Gamma times imbalance of F. Okay, so if F is very unbalanced, this error is going to be small. Okay.
Zero, right? Imbalance of F could be zero.
What?
Imbalance of F could be zero.
Yeah, so in the second part, we'll prove that balanced functions are also pulled by this, so we can just ignore the case. I mean, we'll have two bounds, one for imbalanced functions and one for balanced functions. And we'll see that if the function is balanced, we can use the other bound. Okay, so let's prove it. So that's like balance of F times the zero. W plus Y. The expectation of the same thing. U instead of W plus Y. And we want to show that this is smaller than the other. Right, because then we take the imbalance to the other side. And this is just the error. So how are we going to do this? We are going to prove that actually we don't need Y. It suffices to use W, and it already pulls imbalanced functions. Okay, and then we'll claim that adding Y doesn't make any difference. Okay, so let's open this. It's in here, and we take it inside the value. So it's path expectation open minus one W plus F of U. Okay, the minus one of it to the F of U comes inside. This is same thing, but with U instead of W. So minus one to the F of U plus F of U prime. We have two copies of uniform variables. And this is just the same distribution as W plus U, right? Because this term is uncorrelated to this term, right? You allow me to write it like this. And we'll do the same here. U plus U.
I understand, like, the same, is it a different copy of Y or the same Y? W, sorry.
It's the same,
That U is.
but you mask it with a random. You mask it with a random element.
Okay.
No matter how correlated the shift is with whatever.
And this is simply the derivative of F in the direction U evaluated on them, right? So it should be read as sample direction and then take the directional derivative of F evaluated on that. And this is the derivative in the direction U of F evaluated on U prime. And now since W pulls the derivatives of F, it pulls for any choice of U, it pulls the directional derivative. So we can take the expectation over u outside. Right? Okay, so we fix first we fix the direction.
Not necessarily right, just
What?
it's just
Yes. I'm not sure. I think it's a summation and
oh
yeah. Yeah, I took the
Go out of the.
minus the same thing with the prime. With so u and here I fix the same u from here. Is it clear? First I sample u and then I evaluate the direction derivative in the direction u. And each one of these elements in the larger expectation is small because w pulls all the directional derivatives. So this is small number and yeah. Okay. So w itself pulls all imbalance functions, but we need to prove that w plus y pulls these functions. So we just add it everywhere and then take the expectation over y outside and we just but then this is the same as f shifted by y and then take the derivative in the direction u. Okay, so it's clear. So since f is closed under shifts, so f plus y is for every fixing of y, f plus y is also in WF, and then taking the derivative gets us to del f, and then w pulls f plus y derivative in the direction. Okay, so w plus y pulls all functions with this arrow. This is a good bound for imbalanced functions. Now let's get to the more interesting part, which is the balanced function. Okay, so f and w and y are all the same as before. And we'll prove that w plus y, this is the lemma balance function. Pulls f with their own imbalance f plus well, yeah, 2 plus delta. Okay. We call that delta is the bias of y, as an epsilon bias said, and gamma is the error of w on the derivatives. W pulls del s with error. Yeah. Okay. Okay. So we want to bound the expectation of plus q plus y minus expectation of which one's differently. Right. So since the function is balanced, we expect this term to be very small. So bounding it by imbalance. Imbalance of F plus of this term only is not a bad bound, right? You could expect that just this is close to zero, so the absolute value is approximately this term, right? So it won't be too bad to take the triangle inequality. Station of that. The same. Okay, so remember we already have this error term. We will only show that this term is small and suffer this.
So this is supposed to be the hard imbalance after.
Yeah, the half term to do.
It says you can reduce the imbalance there to half imbalance.
Oh no, we'll have another half. Another. Okay, so let's bound only this cell. So equation over W this. So
Shouldn't you have an expectation over y?
yeah, that W and here. So I'll take the square of this term and bound it. So this is just a trick that I have, nothing smart to tell about it. It's Jensen inequality. So this is more or less than or equal to expectation of W, expectation Y. Well. Okay, so we first fix W and then analyze the expectation over Y squared. And this is equal to expectation over W, expectations over Y and Y. One. One. What's happening here? So if we open this to sum, we have two sums over the square makes it two sums. So we have two copies of like we have sum over Y times sum over Y. Right? So when we open the parentheses, we get two copies, like two distinct copies of Y. And another way to write this function is there in the direction one
Y minus four.
Y plus Y prime of F plus 1. Okay, so that's the trick because the inputs to the function, these are by Y plus Y prime. And in order to have one here and one there, we just have to shift F by Y.
Validated that.
Validated. Right? What can we say about this?
That Y equals something. Oh, W equals. I don't think W equals the
Hmm? Yes, we want to see. It is the same, let's continue.
Notice the sound. Oh,
Okay,
yeah.
Oh,
Computer is not very.
Y, Y,
I'm actually not sure the
Station of the W.
protein and the C.
Minus 1 to then y plus y prime.
If we can't see it, and I'm
Oh,
not.
that's pretty much. No, yeah, sure, we can- send it. So this is the same as multiplication over y and y prime. Multiplication over w of minus 1 to the y plus y prime. F plus y over w. And since w fools these functions, these functions with O gamma, this is not too far from replacing w by u, right? The only update now. Clear? Two. Oh, yeah, two is just because of the difference between the 0, 1 arrow or the plus minus 1 arrow. So it's not really important, just when I did it at home, I get part of the forest normalization. It's not my work, it's Viola's work.
Oh, that's another kind of balance, right?
No,
No.
this is, oh, this one?
Yeah.
So this one is,
Oh, no, it's a directional balance.
yes, so let's see. So let's like this one as, let's open this back to F of U plus Y plus F of U plus Y, right? But this has the same distribution as this one. Right? Okay. And this one is this thing must be small because we have a claim that says so. Yes, no? Okay. So what we do here, we evaluate f on a uniform point, but then we evaluate it again on a shifted point, and we want to claim that this has some relation to the balance of f. We don't have much time here, but I prove the following claim. So let G be a function from U to plus minus 1 and H be a function over 2n bits, 2 plus minus 1, which is written as H of x y. Can you see? Equal to G of x times G of y. So these are the conditions. If we have a function H over 2n bits, which can be expressed as the multiplication of G of the first half bits and second half bits, then U plus Y. Equals H. With now, well, Y is epsilon bias. Okay, how should we read this claim? So if H has this form, then we can recycle the purely random bits only by XORing them with an epsilon bias set. So epsilon bias set allow us to recycle random bits. This is a way to read the network. So I think we'll prove this. This function is of the form g of like minus 1 to the f of x. This is g of x, and then we plug g on u, and then g on this epsilon biased set with bias delta squared. Remember, when we add two biased sets, we improve the bias. So let's call it Z. Not to confuse it. And this is going to tell us that this is pulled by taking u here and u plus z here. And the claim says that this is close to 0. I'll skip the details because we don't have much time. But I think this claim is worth proving. So we'll go there. And this is basically the end of the proof. There is nothing much to be seen. Okay, because then we apply the claim here. This is small, and we plug the errors and get the. Get this. Okay, so let's put the.
Where do we get the additional half imbalance?
So this is bounded
That's
by.
fine because you have a square.
Oh, right.
Yeah,
That's actually exactly the difference.
imbalance.
Half and you have the square.
Well, plus. So this is the result, but then remember that
No. What? No. No, you get delta squared. You don't get imbalance squared. Why do you get imbalance?
also get as delta squared.
Where did you get the imbalance squared?
Oh, because delta squared is our thing, but you have
Yes.
and you don't have the minus.
Oh, you.
It's the same thing we did beforehand.
Oh, right.
The imbalance comes from replacing this by u prime, because this claim tells us that we fool functions of this type, but fooling them doesn't mean that their expectation is zero. Their expectation is imbalance squared, but because that we bounded the expectation squared, so we need to take the square root of this, and then we plug it down. Okay, so we have 2 minutes for the claim. So this is the Fourier analysis finally.
Yeah.
Okay, so let's define h of x. What's expectation over u of g u g x. So this may became familiar. This is a convolution when we talk about the reals. And let's analyze h hat of s, the Fourier coefficients of this function. So what's the Fourier coefficients of convolution, G convolution G? Do you know it from the slope?
It's not multiplication.
Yeah, so it should be just G hat of s squared. We're going to prove. So the Fourier coefficient corresponding to S is just expectation of H multiplied by the factor. So it's G U G over U plus X. And then we need to take multiplication over X with chi S over X. Okay, so let me just write it as U prime. Right, this is the definition of the Fourier coefficient. And then this has the same distribution as this. Okay, I just moved the, I mean, we have in this form, we have like two independent copies and then their sum. So let's just write it as two independent copies and then their sum. Okay. And chi
It's multiplicative.
yeah, it's multiplicative, so it's chi S of U times chi S of prime. And since U and U prime are independent, so it's just U times chi S of U. Right, we have one with this form and one with the prime, which is the same. This is the same thing. Okay, so we have the Fourier coefficients of H. And so the L1 norm of H is just sum of G at square, which is just one, right? Which is just the norm of G, which is one. Right, the Parseval identity, and one because this is a 0, 1, the plus minus one function. Okay, so H has a small L1 and epsilon bias sets full functions with low L1 norm. Okay,
What's the last say?
this one,
Yeah.
the norm of G squared, it's one. Why? Because G,
What no?
but this Parseval identity tells us that
No,
sum,
Parseval is fine. I don't. Yeah.
this one,
But continue.
not just because it's a Boolean function.
The real
It's a function to plus minus one. What's the definition of the norm G? Just evaluate in every point, which is plus or minus one, and take the square, which is always one. Then take the expectation.
Okay.
Okay, sorry, we're a little late, 1 minute late, but okay, so epsilon bias sets full H. And we want to prove that they full H, this H. But this is just H of Y. I mean, we want to show that epsilon bias sets can be used to recycle randomness. Okay, so H of Y is simply as H and U and so on. Okay, so this ends the